All right, diving in today. Proteases. You know, those enzymes that break down proteins. We got some material, some really interesting stuff, actually, on how they're made and all the amazing things they're used for. And, well, it's a lot to unpack, but that's what we're here for, to, kind of distill it down to the most fascinating and useful bits.
Yeah, definitely. And the first thing to remember is that they're catalysts, proteases, and they just speed up the breakdown of protein, cutting those bonds. And the fact that they're a major industrial enzyme, I mean, that tells you something.
Right. So, okay, where do they even come from, these little protein cutters? Seems we have tiny organisms to thank, right?
Yeah, you got it. Microorganisms, bacteria, fungi, actinomycetes, these are the real heroes.
Okay, so let's break that down a bit. Bacteria first.
Sure. So a bacteria, and specifically, Bacillus species, like B. subtilis, the usual suspects. These guys are really good at pumping out what we call alkaline proteases.
Alkaline protease. Okay.
Yeah, and those are the ones you find in like laundry detergent. They break down those protein stains. And what's really cool is that these bacillus, they're really good at secreting these enzymes.
Oh, wow. So they just pump them out. And the fungi, what about them?
Okay, so fungi. Now, these guys, especially Aspergillus niger, they're key for making acid proteases. Now, these have whole different applications, and what's great is that A. niger, it's considered safe for, anything food-related. And like Bacillus, it's also a superstar at secreting enzymes.
Gotcha. So we got the bacteria, we got the fungi. Now what about those actinomycetes? What are they bringing to the party?
Oh, yeah, the actinomycetes. Well, those guys, think Streptomyces. Streptomyces grueus, for example, they're known for their extracellular proteases, which are used in, things like leather processing.
Interesting. So the choice of which microbe to use, it really all boils down to what kind of protease you need.
Right.
Its ideal working conditions and, what job it needs to do.
Yeah, exactly. I mean, you wouldn't use a hammer to screw in a light bulb, right?
Right. Makes sense. Okay, so you've picked your organism. Now you need them to make lots of these proteases, right? Like on an industrial scale. The material mentions fermentation.
Exactly. And there are two ways to do it. Submerged fermentation, SMF we call it, and then solid state fermentation, SSF.
Okay. SMF, SSF.
Yeah.
Got it. What's the difference?
Well, SMF, it's like imagine growing your microbes in a big vat of liquid, a broth, we call it. It's got all the nutrients they need, carbon sources like sugars, nitrogen sources, think soybean meal, things like that. And of course, you got to throw in some minerals too, keep them healthy.
Makes sense. So it's all about, like, creating the perfect environment for them to thrive and produce those proteases.
Absolutely. You want them happy and productive, so it's usually a batch process. Or sometimes a fed batch, where you add nutrients over time to, really crank up the production. Oxygen is super important. And then you got to keep the temperature just right, kind of like body temperature for bacillus, a little cooler for fungi. And then, pH control is key. For those detergent enzymes, you want things a bit on the alkaline side.
Alkaline.
Right.
Right. All that mixing, that's to make sure everything's distributed.
Exactly. You want those nutrients and oxygen to reach every little microbe in there. No one gets left behind.
Okay, so that's SMF, the liquid approach.
Mm-hmm.
Now, what about SSF, solid state?
Okay, SSF, it's a whole different scene.
Yeah.
Here, you're growing the microbes on solid material. But it's moist, it's not bone dry. It's often like agricultural byproducts, like wheat bran, things like that.
Oh, interesting. So they actually grow on the material itself.
Yeah, and it acts as both the support and the food source. It's pretty cool. Now, moisture control, that's super important here. Oxygen is still needed, of course, but the pH, we usually don't actively control it.
Okay.
And this method often uses fungi, like our friend Aspergillus. And, one thing about SSF, it can take a bit longer.
Longer, huh? So more of a slow burn.
Okay.
So we've got our microbes. They've done their thing. They've made our proteases. What happens next? How do we actually get the protease out and make it usable, for all these applications?
So that's downstream processing. So first, you got to get rid of the microbial cells, right? They've served their purpose. We usually use centrifugation or filtration for that.
Okay, so we're separating out the cells.
Right. And then we got to concentrate the protease. There are a few ways to do that. You can use filters, special ones called ultrafiltration membranes, or you can make the protease precipitate out of the solution, kind of force it out. That often involves using something like ammonium sulfate or a solvent.
So now it's more concentrated.
Yep. And if you want a really pure form, you can go a step further and use chromatography. That's a whole other topic. But basically, it's a way to separate out the protease from any other molecules that might be hanging around. You can do it based on size, charge, or even how well it binds to specific things.
So it's like a super fine-tuned separation process.
Exactly. And finally, you got to formulate the protease into a stable product, something that can
Hmm.
be stored and transported without, losing its activity. That often involves drying it, like spray drying or freeze drying. And sometimes we add stabilizers to, keep it happy. The final product can be a liquid or a solid, depending on what it's going to be used for.
Wow, that's a whole journey.
Eh,
From tiny microbes to, a finished product. It's amazing. And speaking of uses, these purified proteases, they really do have so many applications. It's mind-boggling.
It really is. I mean, we've already talked about those alkaline proteases in detergents. Breaking down those protein stains makes life so much easier. But then you've got the food industry. They use proteases for, like, improving bread texture, making it nice and soft,
Oh, right, right.
and tenderizing meat. There's specific protease for that. Papain, bromelain, phycin, they all come from plants, actually.
Interesting. So it's not just microbes doing all the work.
Nope. Nature's got all kinds of tools. And in cheese making, they use proteases to, like, curdle the milk. That's how you get those solid curds. Traditionally, they used rennet, which comes from calf stomachs, but now they often use microbial rennet, which is, made by
Ah,
microbes.
so it's like a vegetarian-friendly version.
Exactly. And even in brewing, they use proteases to prevent haze and make the beer nice and clear.
Wow. I never would have thought of that. So it's detergents, food, what else?
Oh, so much more. The leather industry, they use proteases for dehairing and beading. That's a process that softens the leather. And in textiles, they use them for things like biopolishing and desizing. It helps give fabrics the, smooth finish.
Interesting. So they're not just breaking things down, they're also kind of refining things.
Yeah, it's all about controlling those protein interactions. And then, there are medical applications too. Some proteases are used as therapeutic enzymes, like for wound debridement, cleaning up those wounds. And some have anti-inflammatory properties.
Really? So they can actually help the body heal.
Yeah, it's pretty amazing. And they're even used in the production of some peptide drugs. So, pharmaceuticals is a big area. And then there's bioremediation, using proteases to break down, like, protein waste. And of course, they're essential tools in research and diagnostics for analyzing proteins, synthesizing peptides, all sorts of things.
It's incredible. Proteases are everywhere, and they're doing so much. So we've seen how different microorganisms can produce these proteases through these two main fermentation methods. And then, after all that downstream processing, we end up with this incredibly versatile tool that impacts our lives in so many ways, often without us even realizing it.
Absolutely. It's a testament to the power of these tiny biological machines.
It really is. And it makes you wonder, considering these intricate microscopic processes that give us such versatile tools for manipulating proteins, what other hidden biological processes are constantly at work, shaping our world in ways we're only just beginning to understand? Fascinating stuff. Thanks for exploring this with me today.
You got it. Always a pleasure.
That's it for this deep dive. Until next time.
See ya.